Thank you very much. It's very nice to be out here. That conference that Gotham mentioned was the NATO conference on thermonuclear supernova, and it was my first introduction to characters, I would say, with big personalities in the field. One of them was your very own Iko Eben, and he was talking about his double degenerate white dwarf merger versus Ken Nemoto's single degenerate hydrogen accretion white dwarf to power type 1a supernova. I now think they're both wrong and they're both right. So that's how far the field has progressed. They wanted, of course, for it to explain everything. Today I'm going to talk about LS4, the Silla Schmidt Southern Survey, sort of where we're at, when we'll get going, and what we hope to accomplish, some of our science goals. And I'm going to finish off with one of my new projects that I've been working on just since December. I get bored very easily and start thinking about working on new things. So, okay, so the who, what, where, how, why, when is what this talk is going to be about. The why. So LSST is not going to be the best thing for transient science. It's going to do a lot, okay? It's going to enable a lot, but it's not going to do everything that I want, okay? And this is just due to the fact that this is a very large program with many, many science drivers, and you're trying to do all of them fairly well, which means you're not going to do an excellent job on any one thing. And that's just the way it is. So the cadence that's where things really get affected, okay? Not all volumes are created equally. Rubin and the LSST program are going to find a lot of things hanging out at 24th magnitude. And there are only so many 10-meter and 30-meter telescopes available to follow those up. So there's a huge play space there for brighter objects. And finally, I think it's been shown very recently, last decade or so, that one survey is not the path forward in transient astrophysics. I'm going to talk about the impact of DESI on this, but you just look at all the different ways people are combining data from projects like WISE and NEO-WISE with the dark energy survey, with DESI, et cetera, and the science just grows and grows. And so it's the complementarity to all of these other projects that I think LS4 really hits a niche. So this is all captured in a paper which just appeared a few weeks ago. Adam Miller is the lead of it, and our focus here is on a shallow survey with higher cadence, which maximizes our easily obtainable follow-up resources. So here I'm talking sort of 4-meter class telescopes and under. I think I hit forward. There we go. Okay. So back in 2020, I was looking at places where we could do a wide field shallow survey in the south. And there are actually only two options unless you wanted to build a telescope. And I wanted to do things very, very cheap. I'll tell you how cheap a little bit later. It was the Silla 1-meter Schmidt and the CTIO half-meter Schmidt. Those were the only ones that could give you a 20-ish square degree field of view, and you could pave over them. And LS4 went with the 1-meter Schmidt just because A, it's a little deeper, and B, had a slightly larger field of view. And if you look at this plot of étendue versus collecting area, it's basically half a Zwicky transient facility. And noticeably, it sort of fills in a niche between where Black Gem is, that's 3 half-meter telescopes that are operating at La Silla, with 10K by 10K CCDs on each one, and DECCAM, okay? And DECCAM will be around for another couple years, and then my guess is the powers that be at DOE will take that telescope over from NSF as well, but who knows? We'll see, we'll see. The cool thing is that La Silla, outfitted this way, nicely fills the gap between HAT-PI, which is a sort of all fisheye lens, all sky survey that's sort of brighter than 13th magnitude, and Rubin, where things start saturating at around 17th magnitude. And we figured out a way to get it on sky by 2025, which was nice, that it was going to be complementary to when things got going with Rubin. So how could we do this, and how could we do this on the cheap? So what we did is figure out where we could get CCDs very, very cheaply. And it turns out that when LBNL made the detectors for the dark energy survey, they made about 200 of them. And Fermilab went through and found the best ones they needed. And so all the rest of them were spares. And a good chunk of them were still science grade. And so we went through and started looking at each of these CCDs in earnest, testing them, and seeing how good they actually were. This is a picture of my graduate student and a couple of folks at Fermilab that he was working with. This is Kenneth Lin. He started the testing very early on in 2021. COVID protocols were still in place, and eventually wound up with 32 science grade CCDs, a couple of science grade spares, and about 8 engineering grade CCDs that we could use for testing. And thank God we did. These are the ones that we put in for testing. And if you'll notice, right here, you see we sort of cut off the edge of these chips right here, okay? And the first time we put the thing down there, things weren't measured to a micron. And so we cracked one of the engineering chips and we said, we should fix that problem, okay? This is what happens when you do things on the cheap. But we were smart enough to do it with the engineering ones, so no biggie. That's what the full focal plane now looks like. The camera was assembled at Yale by David Rubinowitz and Charlie Baltet. They've done this quite a few times with some chips exactly the same. They did the Mosaic survey on the Kitt Peak telescope in Z-band in the north before DESI got going to get all their targets in the north. And they built that camera. They went from nothing to completed camera and functioning in 1 year, and then 6 months later, the whole survey was done. So, okay, so this is one of the things on the volume. Roughly speaking, I wanted a volume so we'd find 1 or 2 cool new things a night, a supernova, okay? And then we'd like it deep enough such that I would have an unbiased sample, that I'd be well below my magnitude limits, that I'd have an unbiased sample to have as a great data set to do rates and things like that, and it wouldn't stress the follow-up resources that we had. That potentially we could get a spectrum of everything if we wanted, or at least the host galaxy at some point. So the cadence. So here are some old plots of what cadence used to look like. People thought in our fits to supernova light curves. And basically, there were some rather large uncertainties. And well, if you get, hundreds of thousands of these things, okay, maybe you can beat things down. But if there are systematics with the type 1a supernova and you need better quality data to see these systematics, and I'll talk about one of them shortly, then maybe this is not what you want. And getting colors at the same time is something that we thought about. Here's a more recent view, and you can see what happens now with Rubin and the LSST survey is that what happens in year 3 is different than in year 4 when things get going. And so the number of visits spread out over the year, for some of these fields, yeah, it might be 200, and that means a visit in some filter, so divide it by, the number of filters they're doing the survey in, and then the next year it might be low, okay? You'll get a bunch here and a bunch there. And so we started to look at these things, and so here's an exemplar of this. So in the start here, you're not getting many observations, but they're very deep, and you got some nice constraints coming from Rubin, non-detections, okay, in GR and I. And then now you have a supernova go off, and this is LS4, and these are sort of our limiting magnitudes here. And then you get this very nice light curve. And then, but that's what we get a year later. But a year later, Rubin actually sees it and is pounding on it, okay? And we get these beautiful late-time light curves that can tell us about basically nuclear radioactive synthesis in the explosion model and positron capture and a whole bunch of different things. It's really going to be this nice synergy between these two projects. I'll talk about some other things that you can do at early and late times that sort of excite me. So this was our thought, was this is how we'll work. We'll take advantage of the deep where we can, and and occasionally we're going to get some wonderfully deep things here as well. What can we do with all of that? So we wanted to be cheap, so no filter wheel, no filter exchanger. So we do fixed filters. The group came up, and I was surprised by this. They did not want to do GRIZ. We bought all 4 filters. They actually wanted to do G and Z and 2 I-band filters. And the reason being is they always wanted to get I-band. The great thing about LS4 is we're using these DECCAM chips. So these are thick CCDs. They have incredible response in the red. So we got the filters. They're perfectly matched to what Rubin has. And they went with this. And primarily it was to always be able to get a color every single night, either I minus Z or G minus I. But the I would always be there. And also to go deeper on I-band. We had a group there that's interested in strongly lensed supernova, and I'll show in a bit how they wanted to push on that and get deeper. So here's an example dither pattern. So this is where things get a little crazy. So you're chunking along like this. You fill in the sky, and then you come back. Okay? And you can see, okay? And now I want to go get all 3 colors on something. And you can see what happens very quickly. I'm doubling up an I, whoop, and getting through everything else. Okay? And it's this that we're actually struggling with right now, is what is the optimal way to do this dither pattern. This was one proposed by Chris Stubbs, yes?
Just going back to your filter design system here.
Yes.
CCDs have crosstalk with each other. And normally when you do a crosstalk correction or something, you find like the bright source in one CCD when
Right.
you're processing the full mosaic at once, and then you correct for the charge that's in a different CCD. But here you've got 4 separate filters, right? So a source in a different CCD is also, you're looking at a different part of the SED itself.
Right.
How do you manage this in your pipeline?
So it's just like anything else in that we'll dither around and do like what they do with the star flats. It's just the crosstalk is just from a different part of the spectrum. It's not going to make, it's no different than the way you do it right now.
Okay.
Yeah. Yeah. Yes?
How long between each of these passes?
45 seconds is the exposure time, 15 seconds is the readout and slew.
Okay.
So about 1 minute
For each exposure.
each footprint. Okay? So,
So
this,
5 minutes or
this
so.
could all be done in 24 minutes.
Okay.
Okay? So in any case, we're still working on exactly what's the optimal one. If anybody has any ideas on how to do this, that would be great. We've done stripes this way. Chris Stubbs proposed this one. I was like, it's as good as anything that I've thought of. You wind up getting edge effects, no matter which way you do it, okay? And that's fine. So it turns out you have to take 23% more observations with a fixed filter to get all 3 colors than you would if you had a filter exchanger or filter wheel. So it's not horrible. We lose 20%, but then we have a part that doesn't break. Okay. Okay. So here are the quick facts. So 20 square degree field of view winds up being, with the gaps and the edges and everything, about 18.7, I think. 4 fixed filters. This is for the first year only. We may decide to switch this moving on. G-band gets to about 21st magnitude, plus or minus a half, depending upon new moon, full moon. Okay? I-band's getting to around 20.6, plus or minus 0.2. And Z-band is just 20th magnitude. The sky's right. It's a short Z-band filter, like the one on Rubin. We went with that because I wanted to be able to do direct comparisons to Rubin data and calibrate on the same thing, rather than getting slightly more signal and slightly more noise by going out to 1 micron. Depending upon how you want to do things, you can cover 2,000 to 4,000 square degrees a night. 90% of it's in what we call the public survey mode. 10% of it is reserved right now, mostly multi-messenger astronomy, but special projects. And we're going to have real-time public data. So here's an example of the extragalactic survey, this 90% of the time. Early light curves coming out from a type 1a supernova, for example. This one, a double detonation model. And you know where the data is and what you could see and what's doable with the supernova at a reasonable redshift. I think this is like 0.04. These are the main topics that people in our collaboration have pulled together: gravitationally lensed supernova, TDEs, F-bots, infant supernova, flash spectroscopy, 1As for cosmology. Alerts publicly streamed. Photometry will be released annually once we do some, quality control. Our design right now is that we're doing a rolling extragalactic survey. G and I, one epoch, I and Z the next. This will be 75% of the time. It'll be broken down into the leg and the foot. And there is something that makes sense of those are actual acronyms. I think this stands for long extragalactic, and this stands for fast optical something transients, okay? So Adam was trying to force it in there in some way. In any case, 4-ish thousand square degrees a night, rolling on like 7,500 square degrees, okay, when you get the overlaps in there. And the foot survey is 1,000, 1,200 square degrees where we'll have a one-day cadence. We'll also spend 25% of the time, primarily during Chilean winter, doing a galactic survey. So that sort of gives you an idea of our footprint. Now, the partnership observations, they're sort of 10% of the open shutter time. So TOOs for MMA were what a lot of the groups who were paying cash for the collaboration wanted to do. And it turns out, well, not in 04, but maybe in 05, when the error circles are smaller on these events, 10% is more than enough time to follow up any reasonable candidate. And you could say for 04, it's infinitely more time. There are also special projects that we're going to be doing. These could be very high cadence, where we're taking 6, 8 observations a night on a subfield. Ultrasat is an Israeli ESA NASA UV telescope, sort of a smallish, under a meter telescope in space, doing a near UV survey, 2,500, 2,000 angstroms, covering about 200, 250 square degrees, 6 months in the north, 6 months in the south. We'll be following up that. Euclid, we're already thinking about how we're going to go on top of that survey. The WHO, okay. So you'll see the timeline. This was very quick. So I reached out to people I knew that weren't involved in ZTF and weren't involved up to their eyeballs with LSST and Rubin, but were interested in extragalactic astronomy. I eventually let some Milky Way people into the group. I had no choice. They sort of hang around on the outside. But also I promised them all the time they wanted during Chilean winter, and because I can't use it, so somebody should. But there is some cool, I actually have been involved in the Milky Way microlensing stuff for a few years now, and it's pretty cool. The main partners, the people who put money, time, et cetera, Berkeley, Fermilab, Northwestern, Tel Aviv, Yale, Millennium, Bar-Ilan, UC Berkeley, and Portsmouth. We have associate members, the token theorist, Abby Poland, and Charlotte Ward, who is actually doing our sort of final supernova photometry pipeline using scene modeling, using a code that was developed by Peter Melchior called Scarlet. Now, Scarlet 2, it's a GPU version. We're definitely going to use it to combine observations from LS4 and Rubin and other surveys, space-based observations, particularly for the lensed supernova. And Chris Stubbs is brought in with his group to do the calibration. So we will have a collimated beam projector and the Stardust work that they're doing to try to get sub% calibration on our photometry. The Collaboration Council is a collection of mostly supernova cosmology folks or lens supernova from a variety of institutes across Europe that were the ESO hook, why ESO would be wanted to get involved in this. GW science is certainly one of the things that we wanted to push on, and something that attracted most of the people in this field was the fact that we had a very red-sensitive CCDs. Because these events start off, well, the one that we know of, starts off very blue and then gets very red. That was something that people were like, being able to go from G to Z on the same night is it drew them to this project immediately. And we liked it on the supernova side because the Z band, basically once you get out to a redshift of 0.1, has shifted into the I band and allows us to do very nice color corrections to handle things like extinction. So this was a main drawer for the partnership folks and the folks at Northwestern, Berkeley, Fermilab, and Tel Aviv. That was the thing that really hooked them. To me, some of the things that interest me were pre-outbursts in supernova. So these have been known for 15 years now. Aran Ofek had a paper on 2010 MC in Nature, 2011 HT, Fraser et al. Basically, it looks like, and this is, we will know this answer with Rubin plus LS4, is that all type 2N narrow line interacting supernova seem to have outbursts in the years before they go supernova. Not unsurprising, they get their narrow lines because the supernova is slamming into some ejected mass. But when we did the rates in PTF, basically we could not exclude, we found something like 30% of them. We had actual detections when we stacked the PTF observations and went deep. And they were occurring, you can see 4 or 5 magnitudes below where they peaked after they went supernova. But there were definitely detections, and sometimes they were gurgling for a month or two before, sometimes it was a year or so, et cetera. But now, with Rubin being able to get to 24th magnitude, so working down here, we'll be able to probe this a lot more. We could not rule out 30%, we had direct evidence. We could not rule out, based upon those observations, that the other 70% weren't doing this as well. But now we'll know. Another interesting aspect is post-shock. So Melissa Graham did this. This was an idea I had right before Melissa went off to Washington. I said, oh, we should put in a proposal to HST to take UV imaging of all of the 91T type 1A supernova to see if they have interactions going on a year later. This was the idea. We had seen, just a few years before this, a 91T like 1A that blew up, looked normal, spectra looked normal, and then all of a sudden it started interacting with something. And then the entire spectrum got washed out, and then these emission lines started to appear, calcium, hydrogen, oxygen. And so what it looked like was that this supernova, hearkening Ken Nemoto's model, looked like a pre-nova outburst had gone off from the progenitor system, and then the supernova exploded and ran into it. And so we saw a normal supernova until that interaction. So I said to Melissa, hey, we should just go get some UV imaging because it'll show up in the UV. And there was a great thing that happened, and I thank the gravitational wave community. There were 2 false alerts that triggered HST to go God knows where, okay? Merging black holes, like they were gonna see anything. But they did what they did, okay? And the thing was, we had a project, we got it approved. I forgot about the idea. Melissa wrote the whole thing up, and like a week before the HST deadline, you want to take a look at the proposal we put? I'm like, what is this on? I had forgotten what I had said to her. And submitted it, we got it, but we weren't getting any of the observations. These 2 events screwed up the whole HST scheduling, and we were a snapshot observation program. We were like, just get us an image in the UV at any time during the year. All of a sudden, all of our observations were scheduled because they just had holes in their calendar and they were looking for anything to stick in there. So we got all the observations done, and then we found this 2015 CP in the UV, and we took spectra of it on X shooter, and we could see the emission line in H alpha. This is almost certainly caused by the magnesium 2800 line being an emission. It faded very quickly. We went back with STIS, and it was gone like less than a month later. But this looks very much like something that happened, just delayed. The nova took place 100 years before instead of 10 years before with the other event that we saw. So it took longer for this one to slam into it. Once again, Rubin can go to 24th magnitude a year after we see these events at lower redshift, and we'll be able to do this in the optical where H alpha will be popping up. Then we'll be able to hone in, is this sort of the definitive progenitor mechanism for this channel of type 1a supernova? So I'm excited about that. Flash spectroscopy. This is a term coined by Avishai Galyam. This was the first time we had observations with PTF where we were getting our turnaround times down to 10 minutes from basically shutter close to alerts available to look at. And so nothing, 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 and then we see this thing screaming up, and we were on Keck that night. We were able to get a spectrum. It showed this wonderful Wolf-Rayet star that was basically the supernova's shock lighting up all the material around it. So we just saw the Wolf-Rayet star, okay? That was it, okay? And then the supernova started to expand, and this turned into a normal-looking supernova right afterwards. But we were able, within 12 hours, to trigger all these instruments in the radio, SWIFT, Keck, you name it, were all triggered. And this is something we definitely want to enable with LS4. And it's one of our main focus is how can we get, for particularly interesting events where we see a large change in brightness in coincident observations during the night to trigger something out of follow-up instrument. Another chunk of this is cosmology. So, of course, standard sirens, you know. Okay, I have to throw that up there because why is the DOE interested in gravitational waves? Okay, but this is the thing that I'm mostly interested in, is peculiar velocities. So A, we're going to have calibration. We hope to get to the same level that the Zwicky transient facility. They have 3,000 some odd 1As on a Hubble diagram that they're getting ready to push out. So they have 3,000 1As in the north, but if you really want to do peculiar velocities, you've got to get a similar sample down south, because you need, the only way to beat down errors and uncertainties are by pushing on the entire sky. And Alex Kim and Eric Linder wrote a very nice paper on testing sort of this measurement of F sigma 8. It's a constraint on general relativity. I think we all know what the answer is, but it is one of the only other ways that you can test general relativity easily these days. The cool thing about this is that out of those 3,000 supernova, to date, all but 250, 300 of them weren't targeted by DESI's Bright Galaxy program. So DESI has a program in there. It started 10 million galaxies, the 10 million brightest galaxies in the extragalactic northern sky. The ones that we didn't get out of those in ZTF were actually ones in the galaxy. Why ZTF bothered following these up, I have no idea. They're like through a magnitude of extinction. In any case, they can test extinction corrections. I don't know what they want to do. But we got almost everything out due to this MOST host program run by Mayan Sumanyak a former postdoc of mine. And so we have beautiful, beautiful measurements there. The other cool thing we can do is we can turn around the supernova measurements, and for every galaxy it occurred in, where we can do the, blanking on the term, fundamental plane measurements, distances to galaxies, which DESI's going to get, okay, we can use the 1As as calibrators on that and hopefully improve the fundamental plane measurements. So we now have 3,000 some odd 1As in galaxies where we're hoping to recalibrate. This then opens up a whole bunch more space. DESI ripped through those 10 million galaxies in the first 3 years. It's now lowered its brightness from 20th magnitude to 20 and a half, and it's tagging on the fainter ones and going through that. We will also have, down in the south, the TIDES Foremost program. Like LS4 is half a ZTF, TIDES Foremost is like half a DESI. 2,500 fibers, you know, but same 4-meter telescope. Other great thing is this collimated beam projector, the Mondrink et al. Paper with Sebastian Bongard, Chris Stubbs, and company. This supernova is all about systematics. It's all about photometric calibration. Rubin's going to be doing its thing. It'd be great to put it on that, but what would be even better is for both of us to be following the same supernova, directly comparing through our independent pipelines to see how well we can do. Okay, lens supernova. So the Zwicky Transient Facility has found 2 lens supernova, okay? Here's a plot in magnitude space, and this is from Townsend et al., just came out, versus the lens redshift. These are all candidates. These are the 2 lenses that are found. You'll notice they're up here. They're very bright. The reason they're very bright is, well, we're biased to finding brighter things, okay? It's Malmquist bias of gravitational lens. These were almost certainly micro or macro lensed on top of the natural lens of the system. These are a whole bunch of candidates for which we did not get spectra of, okay? But there are about 6 of them that I think look really good due to the light curves. Looks like you have one type 1A supernova going off and then you see another one, or a 2P and then another 2P. So they sort of look realistic. The interesting thing is Nikki went through and in the paper this year looked at why was ZTF finding these and not getting on top of these? Well, okay, these are fainter. That's one thing. The other thing is, though, that ZTF didn't go deep. So ZTF has thin CCDs. The I-band is crap compared to their GNR, okay? And what Nikki said, and this is for Rubin, she was saying if we got a sample to magnitude 22.5, we could get 10 really superb, with time delays around 10 days between each of the images, events each year from Rubin, okay? But the other thing you can just look and see is screaming up here is just the rate of these events. These are the normal ones in blue, the unlensed ones, and these are the lensed ones. And so even at magnitude 22, you're finding a lot more than what ZTF was only working in this regime, and they're not even the good ones. You can't do any custom. These are like 1 hour, 24-hour time delays, things like that. There's not much you can do with these. You need something like 10 days. So the hope here is that we're going to be on a field with I-band every night. I-band's going to about 20.6 in the average, gray time. You get a week's worth of data, okay? You're now knocking on the door of 22nd magnitude signal to noise of 5. So we can stack a week's worth of data. The other cool thing is Euclid is now finding about 1 lensed galaxy per square degree. I wish I was allowed to show you the data, but it's not. You can go and see the ones that they've let out, okay? They're stunning, absolutely stunning. We're going to know where most of the lens galaxies are on the sky. So all we need to do is find a blip there, and we've got a 50-50 chance of it being a lens. It's either in the lens, okay, well, you'll find a supernova in the lens, but sometimes it'll be in the source, and it'll be a lens supernova. So we're working hard on that. Galactic stuff, microlensing, the sort of microlensing versus parallax measurements that Jessica Liu does, where basically as you climb up, you know, let's call it a black hole, the star's going behind the black hole, and you shift due to parallax during the night, you know, you get this wobble such that right when you're near the peak there, you get this little doot, doot, up and down as the Earth is moving and that star's position relative to the black hole is moving. And so you can see that both astrometrically and photometrically. And so these are the things that we would like to be able to trigger on. These events, black hole ones, take a year plus. So this is long time monitoring of the galactic fields to do this. Once again, the red sensitive CCDs really help you in this endeavor. So alerts, we're making 90% of this available. They'll be streamed to the 3 major brokers via the folks here. It's very nice they're doing this for us because we don't want to set up separate ones. So we're just gonna aim the fire hose at Gotham and say, spread the good news to the rest of the world. We're gonna work hard at folding in with the Rubin data streams to provide added value. So if Rubin says it saw something at 24th magnitude the night before, and now we see something at 19th magnitude, we will make that known. And we're also going to work hard to provide added value stacks of data for our lensing for other things. Pipeline folks, Rob Knopp's the main guy. Guy Neer worked on this for a year or so. I did everything for PTF, basically by myself. And then in 2012, we shut down PTF and started PTF2. And I said, Yikao, rewrite the entire pipeline. And we have a pipeline, and we could go with it. But I said to Rob, burn the whole thing down, start from scratch. He's done it. This is sort of the goals of what we're after here. Less than 10 minutes, extragalactic fields only. Parallelize over chips to get this done. Allow this to run anywhere. Okay, that's what we want. Modularize so we can plug and play with different algorithms. There are many different varieties of subtraction software out there. People like them for different things. We wanted to be flexible. And we wanted to be able to reprocess the data with different parameters, different code versions, et cetera, to see which one was optimal and then go with that. And then keep track of all that, the provenance. This is sort of what the pipeline looks like. Cool thing here, fake injection is occurring constantly. The reason being, I worked with Mark Sullivan's graduate student, Chris Frohmeyer. He did the rates for PTF. You will not see a rates paper out of ZTF. I will tell you why. It's a lot of hard work, and they did not prepare for it, nor do they have the patience to do it. We're starting with fake injections immediately into the software framework of all different types put down on galaxies so that we can see what's going on, so we can get these rates done correctly. I want to do them for all types of supernova. The data flow, like I said, it's going out here, public alerts service. We'll have our internal things using Josh Bloom's Sky Portal. That was Berkeley's major contribution to this. And then we'll have a data archive. ESO will be collecting the data as well. Like I said, the key part, provenance here. One of the things that I wanted to highlight here, let's see if it's, I have it here. Yes, right here. This is my nod to NCSA. NERSC spin. So many years ago during the Dark Energy Survey, Don reached out to me and said, hey, we're having an issue. We're totally fine with the processing for DES. we're having some issues with the reprocessing. They keep asking for more and way more than they had budgeted. Any way we could do this at NERSC? And I said, yeah, sure. Well, I do pipelines like this at NERSC all the time. And we looked at this code, and we started moving the code over here, and we worked with the folks, and this went on for a month. And they were like, we can't do it. And then I looked at their code, and it was like my code at the time, which is why I burned it down and rewrote it. But it was Bash, it was Perl, it was Python, it was C++, it was everything and anything, okay? And they said, this isn't working. And I happened to have a conversation with Shane Cannon at NERSC that day. And he said, well, we have the old Carver cluster. Maybe I can get them set up there. And he said, but wait, I have a better idea. There's this new thing called Docker out there that we could use to manage the images. And he's like, we just need to fix it so that when they're root on the image, they're not root on the entire NERSC system. So they have to be a user on the NERSC system. So basically in 2 nights of coding in Go, Shane wrote the first version of what would become Shifter. There's now Singularity. But these are basically how you run containerized images at a HPC center. We gave that to the folks at NCSA, said, try this. They literally had all the bugs worked out, and they were done by the end of the week, and they were running at NERSC using the Carver resources. They were the first folks to take advantage of this service. It's now a generic service that we spin up at NERSC. It's sort of our cloud computing. The cool thing is it can talk to the big iron through the community file system. It can launch jobs there. Everything that we do is containerized on an image. We want to be able to make this pipeline called C change available to anybody. You can go to the GitHub site and grab it yourself. Follow up, and then I'm going to wind up with my sort of future hopeful idea on cool new science. DESI and Tides foremost. There's an active supernova program in DESI now, so DESI will do its pointings. If you have a target for it that are in those pointings during the night, it takes 20-minute images, 15, 20-minute images, depending if bright or dark time, okay? It will move 1 or 2 or 3 or 4 of those fibers to get whatever you want in real time. So there's that. Tides foremost should be complete by the end of the year. That should be happening as well, but they're going to get the host galaxies of everything, and that's critical for a lot of our science. So that's huge. The other one is SOX. This is another instrument that's just going on at La Silla right now, son of X Shooter. We're going to be passing on to them everything that we get that looks interesting as a bright young supernova candidate. SOX runs 50% of the time. The other 50% is available for ESO. I think we've applied for as much of it as we possibly can get. The cool thing is they do the observations for you. So we just get spectra in the morning. Okay, this is the timeline. 2017, I discussed with Sri Kulkarni about moving the PTF camera down to La Silla. He ran into some trouble. I'll see, Sri talking with other people often causes trouble. So that sort of hit a dead wall. March in 2020, surprisingly, I got bored. So I tried to figure out how to do a ZTF-like survey in the South on the cheap. And by August of 2020, I had submitted a proposal to ESO about redoing the Silla Schmidt down there. So I got the whole collaboration together in these months. Everybody signed on. Zoom was wonderful for this, and everybody had a lot of free time. We started CCD testing at Fermilab in 2021. 2022, we got final approval from ESO and the MOU signed between us and them. By December of 2023, all science grade CCDs were obtained. This was the thing that we said to ESO, cost neutral, will have no impact on the site observations, will provide something that's complementary to everything they're going, and something unique that they currently don't have. They liked it all. They liked it so much, and that we were public, they're basically charging us $50,000 a year to rent the telescope. So it's quite nice of them. We fully assembled the camera in May. All the testing of it was complete by December. We shipped the camera in January of this year to Chile. This is them in March doing the first pass, figuring out all the things that we need. We need about another $40,000 worth of equipment, which we expected. We expected more like 50, so we're under budget there. We'll start commissioning in May. Survey, this is like a soft opening. We're going to do some reference fields. We're going to find some stuff. We're going to test our pipelines, things like that. First alerts, we expect July. Once again, testing phase. We're going to aim the fire hose. They're going to tell us too much, too little. And then we're going to discover a LIGO counterpart right before the end of 04. Yeah! God, that would be so good if it was us and not Rubin and not ZTF. It would just be like, and no, this is all funded by private money. DOE loaned us the CCDs. They don't want to do anything with this project other than take advantage of it. So they don't want to pay for anything, okay? All right, future fun follow-up. This is the last couple minutes here. I just wanted to throw this out there. Okay, resolution in the optical, okay? Diffraction limit, you guys have probably seen this. So if you want to resolve something that's 10 micro arc seconds, you need a 4.2 kilometer mirror. And a lot of adaptive optics because the atmosphere is just nasty. So this is not cool. But there's something that I did not know about until November last year called optical intensity interferometry. And I shame my graduate professors that I didn't learn about this. It's known as intensity interferometry, the Hanbury-Brown and Twiss effect. It's from 1954. This is the foundation in which quantum optics sits on, is this effect, okay? The idea is that you cross-correlate photon counts from two telescopes, okay? I'll show why on the next slide how this works. You have to have fast detectors, around 10 picoseconds, and synchronization, sort of like 100 picoseconds. Amplitude interferometry, the one that I knew about, that I was taught in grad, sort of amplitude phase interferometry where you actually combine the beams and then you tweak the distances till things line up, okay? There's another way to do this by distributing quantum entangled photons, okay? It's crazy, but this is the one I'm thinking about. This is Hanbury-Brown and Twiss's experiment at the Nairobi facility. Two 6-meter telescopes on train tracks so they could move them around and get different separations. These were crude telescopes. They were light buckets, okay? Think Cherenkov arrays, okay? Things like that, okay? They had a station here, and the idea is this. It's called photon bunching, okay? If you have a chaotic or thermal source, it tends to emit things in a non-Poissonian way, okay? They come out in bunches, okay? And so you can use that because you'll emit a bunch of photons here, and this guy will see it, and this guy will see it, and there'll be a different timing than a photon bunch from here, okay? Just due to the angle of the star, okay? That's all it is. So you just got to, where do you get photon bunching from? Any chaotic, any thermal source naturally produces photon bunching, and these are photons that are exactly the same. For all intents and purposes, these are entangled photons. They share the same phase and amplitude as they're coming to you. And so all you do is sit there and time the photons at each telescope, and then you look at the correlation function. You're just doing an FFT at the end of the day between these two data streams. That's it, okay? And they did this. They actually got shamed. Go read it. It's a very interesting. They got shamed by the particle physics community saying they were off their rocker. This is not actually what was doing. They measured the size of Sirius, okay? They measured 30, 40 other stars, okay? This was in the 50s and 60s, okay? And then it stopped. And why did it stop? basically because they couldn't get detectors that were faster. And so what do? You're bunching multiple photons together, and it's harder and harder to pull out that signal, okay? So now people are starting to do this in a whole bunch of places. Cherenkov arrays, they're talking about hooking up Keck and CFHT to measure the size of Sirius B, the white dwarf, okay? There's a program approved that's there. They're now doing quantum key distribution test beds, which can get down to 10 picosecond timing resolution. If you push this, and we're starting to get the fiber put in at the Lick Observatory to do this, you can study a whole bunch of things, and there are white papers on this that are out there right now. One of the ones I liked is resolved novae and supernovae, and we just had a paper here. Alex, Kim, and I, Jack was on it here, about could you do this with supernova? And if you have a 10-kilometer baseline, two 10-meter telescopes, 10 20-second picosecond resolution, and spectroscopic resolution of R of 1,000 is all you need, you can actually measure the size of a supernova, micro arc seconds, expanding in a galaxy that's 15 megaparsecs away. Now, the cool thing about supernova is they have homologous expansion. R is equal to the velocity times time. So I make a few measurements, and I get a direct distance to that supernova. So this is what I want to do as I get ready for retirement, okay? So, and I'll end there. Thanks.